Okay, so welcome back to another video. Today we have a trigonometric integral consisting of cosine of x times the square root of the natural log of cosecant square x divided by 2 dx, ranging from our bounds of integration between from 0 to pi over 4. So today's not going to be that as long of a video, but the work itself is actually pretty complex. So you can probably, as you can guess, there's some trigonometric functions, but also the thing is that there's a u-substitution that lies within the work that we're going to be using. I know a lot of integrals I cover, you always use substitution, but it is indeed like the step we will be using. Although the thing is, before we get to that step, there's actually some rules we're going to have to apply of the natural log, specifically for the natural log properties. As you can see, we have a natural log function inside of our, radical. The whole workload of this entire thing lies mainly because of the u-substitution. You could probably see as well we go through the process that a lot of stuff is just all trying to fix this one substitution in order to get everything into an integral that's actually easily integrable. To a sense that way, not exactly easily integrable, but to the point that we can actually, as it follows with an integral representation, that we can actually use a special formula that's involved in order to get the answer that we want to achieve. So it lies between that. A lot of things I just, lay out the works of it. And yeah, with that, why don't we actually just jump right in? So as mentioned, there's a natural log of inside, there's a trigonometric function. So also mentioning that I should have put in before we start that there will be some trigonometric identities we will be utilizing, especially during the whole u-substitution, debacle. You'll see where I'm coming from with this. Okay, so starting off, let's actually rewrite our integral over here. So I first have 0 and then pi over 4 of cosine of x. Then I have the natural log cosecant square x divided by 2. There's a nice little identity involving the cosecant square x identity we can rewrite this as, and putting this together, we would simplify this to have the natural log of 1 and then divided by 1 minus cosine of 2x. We close that off over here. Okay, I'm gonna draw that line out a little bit too long. Okay, so right there. And then what we can do is, as mentioned, there will be some natural log properties we will be utilizing to simplify this. As you can see, I have a natural log of the 1 divided by 1 minus cosine of 2x. You can guess that this is, division of the argument. So that means we have to do a subtraction of natural logs. As you can guess, natural log of 1 is just 0. And so we have to subtract the natural log of this denominator over here, so this reduces to 0, then pi divided by 4 of cosine of x multiplied by the square root of negative the natural log of 1 minus cosine of 2x over here. All right, then as mentioned, let's actually perform our nice little u-sub. So what will be our u that we will be setting equal to? Let u equals the inside of our radical function. So let me make some space over here. So we're gonna let u equals the negative natural log of 1 minus cosine of 2x over here. Okay, so why don't we actually fix this up just a bit, because I have a natural log function. Why don't we actually get rid of that? So that means I would have to take the e base. Before I do that, let's actually divide the -1 to both sides and then take the e base, which yields us with just e to the negative u, which is equal to 1 minus cosine of 2x. Okay, so let's actually differentiate this. So we have negative e to the negative u, then du is then just going to equal, so apply the trigonometric, so the chain rule over here. So that means this is going to be minus, and then cosine derivative of that is going to be negative sine. So that means, so that'd be a positive, and then differentiate the inside. So that's going to be 2. So we're left with 2 times sine of 2x and then dx. Of course, we want it so that we can get dx by itself. So simply, let's just divide this by both sides. So e to the negative u, and then divided by 2 sine of 2x. So du is then equal to dx. But we can't actually just substitute this back yet, because we have an x and follow in terms of u. So we have to change this so that the denominator is in a form of u. So how do we actually achieve this? This is where I mentioned that the whole debacle with the whole substitution going on, because this is actually going to get a little complicated from here, but it will be further simply explained just by doing the following. So here's what we're going to do. So going back to the e to the negative u equals 1 minus cosine of 2x. So let me actually just put that star just to reiterate where we're actually taking into this direction. 1 minus cosine of 2x over here. Okay, so this actually follows a nice little formula. This is the same thing, slash identity. That's the same thing written as 2 times sine square of x. So if we're just looking at just the leftmost and the rightmost side, so let's actually divide 2 to both sides, so I just get sine square of x by itself. So e to the negative u, then divided by 2, set this equal to sine square of x. So now, if let's just say I just want sine of x by itself, so I'll just take the square root of both sides, yielding us with sine of x is then just going to equal to just 1 divided by the square root of 2, and then multiply by e to the power negative u, and then divided by 2. Okay, so where is this going? I have a sine x, then it's set to equal to this value. Well, let's actually draw ourselves a nice little triangle over here to illustrate this, to better demonstrate this a little better. So a right triangle as we see over here, but then I have in the angle over here x, so I take sine of x, that being of course the opposite over the hypotenuse. So if you actually place things into the correct spot, we have e to the negative u divided by 2 on this side, and then our hypotenuse is going to be the square root of 2. But we need to fill in what this form is going to be, or this side is going to be, the adjacent. This will actually come in handy later because we're actually going to be, this is where that step is going to come in handy eventually once we solve, for our little values. So doing all this by applying Pythagorean's theorem, of course, this is very straightforward, so I'm just going to skip the calculations. If you solve for this side, you're going to get that this side over here, the adjacent side, is going to be 2 minus e to the negative u, the square root of the entirety of that. Okay, so now with that in mind, so now let's actually go back to the original differential that we were trying to solve for, dx. So if to reiterate, dx is going to equal to negative e to the negative u, and so we so far said that this is 2 sine of 2x and then du. So let's actually plug the pieces back together. So, and I'll actually do a separate calculation over here. This side's fine. So sine of, or 2 times sine of 2x. So in other words, sine of 2x actually follows a nice little identity that's the same thing as 2 times sine of x times cosine of x. So in other words, I have 4 times sine of x and then cosine of x. Well, we just solved the value for sine of x, and guess what? Cosine of x is where we're going to be needed, but we actually solved for that side, so we can actually just substitute the values from there. So by doing all this, so in other words, this is equal to, so putting this together, I have 4 then times the sine of x value over here, which is going to be, so what is it, 1 divided by the square root of 2, and then e to the negative u divided by 2, so square root of 2 divided by square root of 2 over here. Then the next thing is the cosine. So we actually solve for the cosine, which is going to be the square root of 2 minus e to negative u, and then divided by the square root of 2. Okay, so let's continue simplifying some things out. So far this is just going to yield us with 2 times e to the negative u divided by 2, and then of course that's the square root of 2's cancel out, so then that's how we got this 2 over here. Then multiply by the square root of 2 minus e to the negative u. Okay, so now continuing forward, that let's actually put back the e to the negative u divided by 2 inside back to the radical. So that'll just be 2 times the square root of e to the negative u, and then times 2 minus e to the negative u. Okay, and then simplify it even further to say that this is the same thing as 2 times the square root of 2 times e to the negative u, and then minus e to the minus 2u. Okay, so with this in mind, this value is going to be substituted for over here. So this is the same thing as e to the negative e to the negative u divided by, where is it, 2 times, and then right here, the 2 times the square root of 2e to the negative u minus e to the minus 2u. Let me actually fix the format of this for a second. After all that, so now we can actually go back to now we can actually substitute the actual differential back into the original, and then we actually already solve, of course, the value for the cosine of x, so we can actually now go back to the original integral. So now putting this back together, I have our new integral. So we change our bounds, of course, for if I plug pi over 4 for x, then that's going to approach 0. If I plug 0, that's going to actually approach positive infinity. So now cosine of x, we actually solve for that value, that this is the value over here. We substitute. So the square root of 2 minus e to the minus u, then divided by the square root of 2. Then next is the square root of, we set this, that's going to equal to just u, so it's going to be times the square root of u. And then the next thing is our dx differential, which is over here, we substitute. So then this is going to be multiplied by negative e to the minus u, and then divided by 2 times the square root of. And then actually another thing is that I can actually substitute this instead, because the next step is we're gonna have to actually go back to do some more substitution. So doing so, I was gonna have e to the minus u and then multiply by 2 minus e to the minus u over here, then follow with du. If you actually do all the substitution over here, so, well, canceling out, that's the word I meant to say. For one thing, square root of 2 and then times 2 from the denominator, that can be factored out. I had to change the bounds, that's a negative, but then that negative cancels out. So then so far we have 1 divided by 2 times the square root of 2 with the integral from 0 to positive infinity. And so this leaves us with, square root of u is going to be the same as it is, and then multiply with simply just e to the power negative u divided by 2, since factoring that out, and then we actually cancel out the in forms of the exponent that we actually utilized fractions. So with that, and then du. Okay, so you think we're done? Well, obviously we're not done yet, but you think that there's still more to go, that we could just leave it the way it is? Not exactly. So now we have to do yet another u substitution. We're actually going to call this value t. So let's see, we're going to let t equals the following. Well, first I should say we're going to let u equals 2 times t. And if I solve for, t by itself, then t is then going to equal to u divided by 2. Then differentiate both sides, so I have that dt is then just going to equal 1/2 then times du. So if I get du by itself, I just multiply 2 to both sides. So then we have the following over here. So new integral. So far 1 divided by 2 times the square root of 2. Then the integral. So actually this is still going to change. This isn't going to change the bounds, thankfully. So 0 to infinity. Then we just substitute this back in. So the square root of 2t. And then now multiply with e to the negative t and then dt. And then multiply by 2 dt. I forgot to put that down. Times 2 dt. Okay, and so with this being the case, that if I just factor out the the radicals, so square root of 2 and then times 2, factor that outside the constant, so that's going to cancel out. So we're just left with the integral from 0 to infinity of just the square root of t, aka I'm going to write this in form of an exponent, so t to the power 1/2, and then times e to the negative t and then dt. Well, guess what? This is actually in a form of a gamma function that we can actually rewrite that as. In other words, if you play around with the exponents carefully and make sure you plug in the formulas, you get that this is the same thing as gamma of 3 divided by 2. And then if you actually put in the values for gamma divided by 2 using that gamma formula, for gamma of some value x is the same thing as x times, or gamma of x plus 1 is equal to x times gamma of x. If you utilize that formula, we're going to get that this is 1/2 times gamma of 1/2, which we know that this is a well-known value. That's just the square root of pi. And so the final answer indeed is just going to be the square root of pi divided by 2. And just like that, that's our final answer to everything to this integral, natural log, trigonometric, hybrid, integral, that everything of all this was utilized just because of this one giant workload of the u substitution. We're actually trying to figure out the substitution specifically from this step. So there you have it. And yeah, that's pretty cool if you ask me.